neuroendocrine response to injury. Patients also respond rapidly to injury by classical neuroendocrine pathways of stress response consisting of afferent nociceptive neurons. The spinal cord, thalamus, hypothalamus, and the pituitary. Nociceptive neurons are excited by the effects of local inflammation as well as by direct injury. The neurons terminate in the hypothalamus and release corticotropin-releasing factors (CRF), CRF stimulants, adrenocorticotropic hormones (ACTH), and release from the anterior pituitary, which then acts on the adrenals to increase the secretion of cortisol within hours of injury. Hypothalamic activation of sympathetic nervous system causes the release of adrenaline, epinephrine, and also stimulates the release of glucagon. An intravenous infusion of cocktail of counter-regulatory hormones, glucagon, glucocorticoids, and catecholamines. It reduces many aspects of metabolic response to injury. The metabolic effect of acute rise in the levels of these hormones is to liberate glucose from carbohydrate stores and to begin the breakdown of fat and proteins as metabolic substrates for energy and repair. There are, however, many other effects, including alterations in the insulin release sensitivity and hypersecretion of prolactin and growth hormone (GH) in the presence of low circulatory insulin like growth factor 1 (IGF-1) and inhibition of peripheral thyroid hormones and gonadal function. Of note, growth hormone has direct lipolytic, insulin antagonizing, and pro-inflammatory properties. Summary 1.2 Summary box 1.2 Neuroendocrine response to injury and critical illness. Neuroendocrine response to severe injury, critical illness is biphasic. Acute phase and chronic phase. Acute phase in hours and chronic phase in days. The acute phase characterized by elevated counter-regulatory hormones like cortisol, glucagon, adrenaline. Changes are thought to be beneficial for short-term survival. Chronic phase associated with hypothalamic suppression and low serum levels of respective target hormones. The changes contribute to chronic wasting. As described above, the innate immune system, principally macrophages, are activated by dams, interacts in a complex manner with the adaptive immune system T cells, B cells, in co-generating the metabolic response to injury. Figure 1.2. Pro-inflammatory cytokines includes IL-1, TNF-alpha, IL-6, and IL-8 are produced within the first 24 hours, act directly on the hypothalamus to cause pyrexia. The cytokines are also augment the hypothalamic stress response and act directly on skeletal muscle to induce proteolysis while inducing acute phase protein production in the liver. Pro-inflammatory cytokines also play a complex role in the development of peripheral insulin resistance. Other important pro-inflammatory mediators include nitric oxide (NO) via inducible nitric oxide synthase (INOS) synthetics, and a variety of prostanoids via cyclooxygenase 2 (OX2). Changes in the organ function, renal hypoperfusion impairment, may be induced by excessive vasoconstriction via endogenic factors such as endothelin-1, complement, and kinin pathways are activated by the process of programmed cell death and phagocytosis. are triggered to clear damaged tissues. There are many complex interactions among the neuroendocrine cytokine metabolic axis. For example, although cortisol is immunosuppressive at high levels, it acts synergistically with IL-6 to produce the hepatic acute phase response. SATH release is enhanced by pro-inflammatory cytokines and the noradrenergic system. The resulting rise in cortisol levels may form a weak feedback loop, attempting to limit the pro-inflammatory stress response. Finally, hyperglycemia may aggravate the inflammatory response in the mitochondria, causing the formation of excess oxygen-free radicals, and also altering gene expression to enhance cytokine production. At molecular level, the changes that accompany systemic inflammation are extremely complex. In one study, using network-based analysis of changes in mRNA expression in leukocytes following exposure to endotoxin, there were changes in the expression of more than 3,700 genes, with over half showing decreased expression and remainder increased expression. The cell surface receptors, signaling mechanism, and transcription factors that initiate these events are also complex. Although the detailed mechanisms are being steadily identified, specific molecular therapies remain elusive and certain subservient to optimal critical care. In this figure, the integrated response to surgical injury in the first 24 to 48 hours, there is a complex interplay between the neuroendocrine stress response and the pro-inflammatory cytokine response of the innate immunity system. ACTH, adrenocorticotropic hormone, GH, growth hormone, IGF, insulin-like growth factor, IL, interleukin, T3, triiodothyronine, TNF-alpha, thyroid, tumor necrosis factor alpha. In this diagram, you will see the brain, the spinal cord. Injury induces afferent receptor pathway, which activates innate immune system, innate immune system, and the immune system. It stimulates the hypothalamus. Hypothalamus releases CRF, and CRF stimulates the pituitary. They release ACTH and growth hormone in the plasma, and this in turn activates the adrenal gland. Adrenal releases adrenaline and cortisols. Sympathetic nervous system stimulated and pancreas it releases glucagon, and innate immunity increases IL-1, TNF-alpha, IL-6, IL-8, also increasing insulin, IGF-1, testosterone, and T3. The changes in body metabolism that results is increased lipolysis and adipocytes increases. Hepatic gluconeogenesis increases. Gluconeogenesis. Skeletal muscle protein degradation also increases. Hepatic acute phase protein synthesis also increases. Pyrexia happens and hypermetabolism occurs. Now, the agonist and antagonist, an uncertain balance. Within hours of upregulation of pro-inflammatory cytokines, endogenous cytokine antagonists enter the circulation, such as IL-1 receptor antagonist, IL-1RA, and TNF soluble receptor, TNF-SR55 and 75. and act to control the initial pro-inflammatory response and limit any systemic organ damage caused by it. A complex further series of adaptive changes includes the development of counter-inflammatory response regulated by IL-4, 5, 9, and 13, and transforming growth factor beta. Within inflamed tissue, the duration and magnitude of acute inflammation as well as the return of homeostasis are influenced by a group of local mediators known as specialized pro-resolving mediators (SPMs), which include essential fatty acid-derived lipoxins, resolvins, protectins, and myosins. This endogenous resolution agonist orchestrate the uptake and the clearance of apoptotic polymorphonuclear neutrophils and microbial particles, reduce pro-inflammatory cytokines and lipid mediators, as well as enhance the removal of cellular debris. Thus, both at the systemic level, endogenous cytokine antagonists earlier, and at the local level, tissue level, the body attempts to limit the inflammatory response, but further tissue damage, sepsis, or other complications challenge the process of resolution. As with initial inflammatory response to tissue injury, it appears that the degree of secondary anti-inflammatory response varies between individuals, probably on genetic basis. If the anti-inflammatory response dominates or is accentuated and prolonged in critical illness, it is characterized as a compensatory anti-inflammatory response syndrome (CARS), resulting in immunosuppression and an increased susceptibility to opportunistic nosocomial infection. For the sepsis, with its associated catabolism results, CARS can be prolonged by ongoing critical illness as a part of ongoing vicious cycle of chronic critical illness, known as persistent inflammation, immunosuppression, and catabolism syndrome. Chronic critical illness syndrome. Thus, both the initial inflammatory response to tissue injury and the secondary modulating response can be seen to differing degrees in different individuals and or at different stages of critical illness. Either circumstances can cause harm and rapid restoration of homeostasis and preventing secondary inflammation or sepsis are key therapeutic principles that influences late outcomes as well as immediate ones. Summary 1.3: The metabolic response to surgery and injury. Key characteristics. 1. Rapid onset derived driven by pro-inflammatory cytokines. For example, IL-1, IL-6, TNF-alpha. Broadly related to injury severity, most severe in sepsis, burn, and major trauma. Varices in severity between individuals. Genetic factor. Causes catabolism, muscle breakdown, immunosuppression, and organ dysfunction failure. Counterbalanced by antagonist response, but the balance may be imperfect. Prolonged by sepsis and other secondary insults. Can be chronic, associated with most late deaths from injury or surgery in developed health systems.